We saw how to use Opamp as amplifier and filter. But Opamps have their origin in analog computers where they were used to perform mathematical operations like addition, subtraction, differentiation and integration. This is Abhinav from learnelectronicsindia.com, and let's learn how to perform mathematical operations using Opamps. To make a summing amplifier, we first need to make an inverting amplifier with a negative feedback. After this, we will connect the supply voltages. After this, we will connect the voltages that needs to be added to the inverting input via resistance and ground the non-inverting input. So the output voltage of the circuit is given by this formula. Hence, by keeping the values of RF and R as same, we can get the sum of the voltages. Now let's keep V1 as 1 volt, V2 as 2 volts and V3 as 4 volts. Hence the output voltage by this formula is minus 7 volts. But as the sign of output voltage is negative, we will add an op-amp with negative feedback of 1 to get the correct sum. After connecting the output of the inverting summer to the input of the inverting op-amp, we get the output voltage as 7 volts. We can change the value of input voltages and observe the output. Now to make a subtractor, we will copy the previous negative feedback amplifier circuit and connect a resistance 1 kilo ohms between the inverting input and V2 and a resistance 1 kilo ohms between the non-inverting input and ground and another 1 kilo ohm resistor between the non-inverting input and V1. To obtain a proper difference, all the resistors should be of the same value. Hence the difference is given by this formula. Now let's set V1 as 7 volts and V2 as 5 volts and run the simulation. We can observe from the output of the multimeter that the output voltage is 7 minus 5, that is 2 volts. We can change the value of input voltages and observe the output. Now to make a differentiator, we will first take a negative feedback op-amp and connect a resistor and capacitor in series with the inverting input. Then we are going to connect a capacitor in the feedback loop. After this, we will connect a function generator to the capacitor C1 and connect an oscilloscope to take the readings. Let's have the value of the capacitors as 1 microfarads and resistor as 1 kilo ohms. The output voltage is given by this formula. We can control the amplification by controlling the values of R and C. In this case, the amplification factor is 10 raised to minus 3. Now let's run the simulation and check the output. So when we give a triangle signal of 1 Hz as the input, the output is a square wave of 1 Hz. You can try giving different inputs and check the differentiated output. To make an integrator, we will connect a resistor and a capacitor in parallel between the output and the inverting input of the op-amp, and connect a resistance between the inverting input and the output of the function generator. The value of C1 is 0.1 microfarads R1 is 150 kilo ohms, R is 15 ohms. The output voltage is given by this formula. The input frequency should be greater than the cutoff frequency. Hence, by the formula, the cutoff frequency is 159 Hz. Now let's give 1 kHz square wave as the input and observe the output. From the output, we can observe that the square wave is integrated to give a triangle wave. We can give different waves as input and observe their integrated output. Such op-amps were used in analog computers to perform mathematical operations and in signal conditioning circuits. You can find detailed explanation along with the multisim file at our website link in the description. This is Avinav from learnelectronicsindia.com and thanks for watching.